Okay, so there are two different kinds of reactions thermodynamically, whether we are using energy or we are releasing energy. Two different kinds of reactions, exothermic reactions and endothermic reactions. Exo means exiting, we are giving energy away. So this is the exothermic reaction, the first one. See that these are the reactants and this is the product. See from here to here, this is the energy axis. Through the energy axis, see, energy has decreased. From here to here, energy has decreased. So this is exothermic. In exothermic reaction, delta H is negative. Reactants have more energy than products. Okay, so the other side, endothermic. See, here reactants and here products. Reactant level to product level, energy has increased. So they have absorbed energy. So that reaction is called endothermic reactions. So delta H is positive. In that, products have more energy than reactants. And y-axis we just name like energy, but x-axis we call it reaction coordinate or reaction progress. Reaction progress explain the meaning. Reaction coordinates are parameters that we can exactly measure to what extent reaction has completed. So as an example, usually we are using microscopic properties for that. If you go with water, let's say using H2 and O2, we are making water. Then bonds of hydrogen, bonds of oxygen, and bonds of water. Bond angles of hydrogen, bond angles of oxygen, bond angle of water, you know, all are getting changed. So those are the best parameters so that to see to what extent reaction has gone through. So that is the reaction coordinates. So then the next one is we are marking the activation energy here. Activation energy is the energy barrier for any reaction, because without it fulfilling the activation energy, it does not complete the reaction. Now you guys know that if we only fulfill the activation energy requirement, we can only go for reactions, chemical reactions. How do we mark activation energy? And you guys know now this is the transition state. This is the transition state for endothermic. Okay, so activation energy, we mark the reactant energy level and the highest energy level, the energy point, energy profile. If we get disconnection here, the level between these two is the activation energy. So that endothermic, this is the initial reactant energy, and this is the highest point. Between these two, this is how you are marking the activation energy. And that you can see obviously, exothermic activation energy is less, but endothermic activation energy is high. So that usually exothermic reactions need less energy to occur than endothermic reactions. So in a way, we can say exothermic reactions are more prone for spontaneity, but not 100%, because not only delta H, but also we have to go through delta S or entropy. Okay, so here I have given these couple of examples for exothermic reactions and endothermic reactions. If the reaction is exothermic, so delta H is negative. If it is endothermic, delta H is positive. Here I'm explaining spontaneity and enthalpy does not have direct relationship unless otherwise known as entropy. Usually, exothermic reactions can be spontaneous, But see, these two reactions are exothermic, but both are non-spontaneous. So it's not always go like that. And also, these two reactions, dissolution of sugar and dissolution of table salts, just annotation missed. Dissolution of these two reactions are endothermic, but still that you guys know, a salt and sugar dissolution are spontaneous. See the endothermic, but spontaneous. That depends on entropy as well. Here I'm explaining what is this reaction coordinate or reaction progress. Any physical property, geometric parameter, which change during conversion of reactants to product. Examples, these are actually microscopic properties, bond angles and bond lengths. Okay, when we are doing calculations, for whatever we are doing calculations, usually for whatever the theory part, we are talking about standards. When we are doing enthalpy calculations, we again need a standards, some sort of a special parameters to consider when we are doing experiments. But before that, we should know what are the factors affecting the enthalpy. So out of these factors, some of these factors we keep in some sort of a level. So that is where converting factors to standard factors. So here, factors affecting enthalpy change are amount of substance, concentration of solution, temperature, pressure, purity of substance, and allotropic form. And then standards are amount of substance supposed to be 1 mole as a standard, because we know that enthalpy depends on amount. So we should get enthalpy as per mole. If it is considering the concentration, comparing to the concentration, solution concentration is supposed to be, for standard condition, 1 moles per cubic decimeter. We cannot talk about a specific temperature because we are measuring the temperature. But usually we consider this temperature to some sort of, let's say, if you are doing the condition in room condition, always it's supposed to be in same room condition. Even we control the condition of the reaction mixture, environmental temperature is supposed to be constant. So that usually we mention even temperature for these calculations. So next one is the pressure. That you know, enthalpy, we measure heat change under pressure. So that pressure is again a parameter, and standard condition mean pressure is supposed to be 1 atm. Then purity of substance is supposed to be 100% pure. And the last thing is the allotropic form. This has two different definitions. Either most common, or most stable. Either of these can be the allotropic form. If we decided one is the allotropic form, then we consider only that is acting as the standard form. As an example, carbon graphite, sulfur rhombic sulfur S8, and oxygen O2, we consider as standard forms of these compounds or elements. But all these three are the most stable in nature. But if we talk about phosphorus, white phosphorus we are taking as a standard, that is the most abundant one. So either we can say most common or stable. Okay, so that this is the definition I have taken from your resource book. Reference form is this, whatever this allotropic form. Element in most stable, almost all the time most stable, but not always. They say in all but a few cases are. there are different few cases, but almost all the time it's more stable, but sometimes it's abundant. At 1 atm pressure and the given temperature, that consider as the reference form. Okay, most important part of this unit is going through these definitions. You may remember, if you're going to remember the definition, each cross, each dot, each dash is really important. It simply means these definitions are exactly supposed to go through the way I'm teaching you. So there are altogether 16 definitions to understand different kinds of enthalpies. If you understand these enthalpies here, going through calculations can be really easy. So here I ask you guys to make this summarization. Then whether it's negative, positive, any special thing you're supposed to write here, you can write here and keep it as a summary of different enthalpies. Okay. I'll explain just one or twice, like, see, each time it is, these Zoom are like, they are updating different stuff, but still, it's still really disturbing. Some people are not talented, I guess. Okay. For a couple of these definitions, I'll explain exactly how it's supposed to be. Rest of the one you can understand well. Okay, so the very first one. We are talking about initial reactants. Whatever the 1 mole of compounds, see, 1 mole of ethanol. Okay, 1 mole of ethanol at standard state. So at standard state, ethanol is in liquid form. Standard pressure and everything, okay? From the reference forms of ethanol supposed to come from carbon, hydrogen, and oxygen. These are the initial naturally existing elements, okay? From these constituent elements in their standard state. So these are the constituent elements: carbon, hydrogen, oxygen. In standard state, hydrogen existing as gas, oxygen existing as gas, carbon we made the standard as, out of these allotropes, carbon solid graphite. But still we have to balance this equation to give all these carbon, hydrogen, and oxygen. But enthalpy associated with formation of 1 mole of compound. So 1 mole of compound means product side always supposed to be 1. So that the full definition is enthalpy associated with formation of 1 mole of compound at standard state from the reference form of the constituent elements in their standard state. Okay. So this can be exothermic or endothermic. If the compound is 100% stable, or that is the reference form, so there are no energy using, no enthalpy using to produce it by itself. Because the formation of more stable form of an element from itself is not changed at all, that is the standard enthalpy of the pure element in its reference form become 0. So that all these conditions, naturally existing constituent elements, enthalpy value become 0. You should remember all these enthalpy, so that is 0. As an example, so our standard for carbon is carbon solid graphite. Formation of solid graphite is 0. See, formation enthalpy of solid graphite is 0, but formation of diamond from graphite, solid diamond, it's not 0. It's plus 1.9. And when we are doing calculations, we are going with symbols. So delta mean difference, H enthalpy, F formation, theta is standard. So that we can write enthalpy change, standard formation. Understood? So you can use standard 0, 5 or whatever. Okay, so once we understand that, going on is really easy. Standard enthalpy of combustion. Now we burn 1 mole with excess O2. Then whatever the products we are just writing. Since you have nitrogen here, you get nitrogen. And usually if it is something that not coming from familiar equations, they are giving us equations. Otherwise, you have to find these equations from whatever the lessons we learned so far. So that you guys know we have to provide always the initial energy for combustion. So it is always, it's releasing, it's burning, it's releasing, it's always giving heat. It is releasing initial heat. So it's always negative or exothermic. Bond dissociation. Okay. So again, enthalpy associated with breaking of bonds of how much? 1 mole of gaseous compound at standard state it convert to constituent elements. So you are making constituent elements by breaking bonds. Okay. So always this side 1. And see, you are breaking also 1 bond. Here, this is very obvious. 1 single bond, double bond or triple bond. But here you are just breaking 1 CH, and that is this. Okay, but let's say that CH4 has 4 identical bonds. But once you break a 1 bond, so its bond lengths, bond angles, everything is rearranging and changed according to Vesper theory, you guys know. So that if there are 4 bonds, when you are breaking 4 different bonds in 4 identical bonds, but once you break one, other 3 are rearranging and changing. So they have different bond energies. So to get then average standard bond dissociation enthalpy, we have to add these 4 together and divide by 4. Then only we can go with average standard bond dissociation enthalpy. And this is a symbol, enthalpy change, standard bond dissociation. D is the dissociation. Neutralization, again, easy. In neutralization, we are getting this enthalpy value as the formation of 1 water molecules, but from aqueous H plus and OH minus, so that this is not formation enthalpy. Enthalpy change associated in formation of 1 mole of liquid water from 1 mole of H plus aqueous ion and 1 mole of OH minus aqueous ions. So delta H theta neutralization. So it is always minus 57 kilojoules per mole. But we are having this issue. If this any acid which is releasing H plus is acids, which is releasing OH minus base, any acid or any base, if it is strong acid or strong base, then they are releasing exactly this amount. But if any of this acid or base is weaker, some of this released energy they are using back for dissociation of this undissociated parts. As an example, let's say we are getting this strong base sodium hydroxide, but here let's say the acid coming through acetic CH3COOH. So this dissociation is weaker. So part is dissociating to give H plus to the medium. So rest of the part to dissociate this as H3COO minus plus H plus. Some of this release energy is using. Some of the released energy is using. so that the value become less than 57. That is the explanation. Okay, I'm going to go on. I guess you can understand this. If you were not in the class, there are a couple of students who came after I did energetics. Here I'm showing the full page, or otherwise you can get this photocopy from one of your friends in the class. Okay, then this part again comes with the, there are different precipitation. Whatever the precipitation comes, it is still the same. But here we are talking about this precipitation while neutralization. So barium hydroxide is a strong acid, sorry, strong base. H2SO4 is strong acid. These two together makes this barium sulfate and water during the neutralization. So they are releasing exactly minus 57, exactly 57 energy they are releasing, but also at the same time they are making this precipitation. See, barium sulfate is a fine heavy precipitate that we did under gravimetry of inorganic chemistry, remember? So that this is also exothermic, so that 57 plus some x value, so the total energy become 57 plus x. So this is greater than normal neutralization energy. So remember that if there's a precipitation, neutralization energy is greater. Then solvation. Solvation means getting dissolved with something. Today, I think they are going through this update. See, the third time this is disturbing annotation. Solvation means getting dissolved in some sort of a solvent. Whatever the solvent, we are writing here solvent, and this is ion. Okay. If that is become water, if the solvent is water, ions get solvated with water, that is hydration. Delta H theta SOV, delta H theta HYD, hydration. During the hydration, ions are get hydrated. You can read and understand this definition. Then the difference between hydration and dissolution. Hydration goes to these ions. Dissolution goes to these compounds. Dissolution goes to these compounds. That is the only difference. Okay, rest of the parts are very easier. Sublimation. Sublimation is going directly from solid to gas, and evaporation is going from liquid to gas, and fusion is going from, it's melting actually, solid to liquid. And number 11 is atomization. You are making atoms from whatsoever. Okay. So this is the atom. You are making the atom, whatever it is, regardless. So enthalpy associated with formation of 1 mole of gaseous atom. 1 mole of gaseous atom from elements at standard state. Okay, see, elements at standard state. Cl2 gas, Br2 liquid, I2 solid. That is the standard conditions of these. But still that you can see, if you go with one Cl2, you are making 2 atoms. So this is dissociation. To get 1 atom, that is atomization. And see the difference here. Solid goes to sodium gas. Still, this is atomization, but also this is sublimation. Sublimation is also same. So that we can write delta H theta atomization for chlorine. Atomization of chlorine equals delta H theta dissociation divided by 2. Or otherwise, we can write delta H theta atomization sodium equals delta H theta sublimation of sodium. So there are connections. Here I have explained a couple of connections here. We did this very nicely, very clearly for theory. I'm not going to explain. I'm not going to waste our time on this because only some students need support. Get support from your friends, or otherwise you can talk to me if you are not understanding these connections. Then the 13th one is the first ionization energy that we did under unit 1 and unit 2. 1 mole of gaseous gives 1 mole of gaseous plus charge. Then the second ionization energy, positive 1 mole gaseous gives positive 1 mole gaseous. Then electron gain energy is the opposite of ionization. Ionization, losing electrons making plus charge. Electron gain, gaining electrons to make minus charge. So gaseous, starting from gaseous, ending from one negative or negative. And remember these points that we did under unit 1 actually. Group 2, 15, 18 elements. First electron gain enthalpy is endothermic process except for phosphorus because they have half and full stable configuration. So delta H Eg1 equals positive. For others, it is an exothermic process. Others can release energy. They don't want excess energy. They do not need energy. This is still the same. Second electron gain energy from uninegative to dinegative. Once you gain one electron density is high. Gaining the second electron makes this electron repulsions greater. So the second ionization energy is always positive. To overcome repulsions, we have to provide energy. Last but not the least, because it's very important, is the lattice dissociation enthalpy. Before 2019, we had lattice formation enthalpy. Now we are doing the dissociation, but regardless, it's same. So if you are writing this dissociation this way, its opposite is the formation. Whatever the numbers they are given, we have to just go with negative and positive of these values, so we can get answers very easily. So 1 mole of a solid ionic compound is converting. Let's say 1 mole of sodium chloride, converting to its gaseous positive and negative ions. See the negative and positive ions. So magnesium oxide dissociates to magnesium 2 plus or 2 minus in gaseous. Aluminium oxide, aluminium 3 plus, oxygen 2 minus, gaseous. This is always positive. This is always positive. Because these are stable. Lattice energy is very stable, that you guys know. If you go through the other way around, sodium plus Cl minus makes NaCl. So these two have these electrostatic interactions, the strongest primary interaction. So they are very stable. So they release energy while making. So if you want to break them, lose them, part them, you have to provide energy. This is the opposite of that, but I'm not giving this. This came through the old syllabus, just I'm giving the idea. So this is the opposite. It's called the formation enthalpy, not the dissociation enthalpy. See the value here, dissociation of sodium chloride is plus 788. Formation become minus 788. Hess's law we are using for calculations. Indirectly we can calculate not knowing the direct value, we can calculate this direct value from this method. Enthalpy changes of a certain process is constant if it is started with same substances, ending with same substances. So regardless the path, net enthalpy change of the process is independent of the route. So if we write, let's say we have two different paths. A goes to B using path C or path C and D. Remember unit 11 mechanisms that we're going to do soon. Some already did. So whatever these different paths, so this, if you go with this delta H1 value, whatever the path, so the value become always delta H1. It's independent of the path. So delta H1 equals delta H2 plus delta H3. Or delta H1 equals delta H 2, 4, and 5. 2, 4, and 5. Both equals to delta H1. See, this is again really important when you are doing calculations. You can get, if you have this knowledge, getting answer is easier. Let's say they were given one reaction to one direction, A goes to B, but we need the enthalpy for the opposite direction. So we are just changing the sign. That is the Lavoisier-Laplace law. When a certain chemical reaction and its backward reaction is considered, same magnitude, only this charge or sign is opposite. Sign is opposite. This is the most important part. If you understand this part, the rest of this energetics is like nothing. That's you guys all know this. I hope you all done energetics, whatever the way, okay? So this is the enthalpy calculations. There are 4 different methods. I'm going to do these 4 different methods again slowly so that you can understand this very nicely. These 4 different methods are as a state function, equation method, thermochemical cycle, energy level diagram. As a state function, you guys already know that. So state function means it's independent from initial and final. It's depending only on initial and final stages, independent from the path or whatever in the path. Okay, so for this given question, consider following thermochemical data to calculate what? See, what is this? Enthalpy change delta H. Standard C mean combustion of what? Benzene in which liquid form. So this is the standard combustion enthalpy change of liquid benzene. They were given 3 data. All the data are formation enthalpies. So formation enthalpy of liquid benzene, formation enthalpy of gaseous carbon dioxide, formation enthalpy of liquid water. They were given these 3 values. This is only they were given. What's the first method? First method is the state function method. State function means we can get this reaction enthalpy by getting the difference between reactants enthalpies and product enthalpies. First, we have to find the aggregation of all the enthalpies of products. Then aggregation of all the enthalpies of reactants. If we get the difference between these two, that is the enthalpy of the reaction. Okay, so this is how you are writing this. So this VP and VR are stoichiometric coefficients of products and reactants. P mean product, R mean reactant. It simply means when we are getting these enthalpy values, we have to multiply with the stoichiometry to get the total value of the given number of molecules. When you are doing a question, this would be really okay. So delta H, this RXN, even R or reaction would mean the whole reaction. And remember this one, usually for the first part, it is going only with the formation enthalpies, but once we're done with this dissociation enthalpies, either formation or dissociation, and also for entropy, and also for Gibbs free energy, we can use this state function method. Other than that, you cannot use. For other enthalpies, you cannot use state function. If you remember this method, if you recall this method, because for the exam, because we get practice a lot for thermochemical cycle and energy level diagram, then you forget this method. Let's say it's an MCQ, so they don't worry about the path you did the answer. So going with this state function method saves your time. Remember that when you are doing the tutorial. Okay, so 3 data were given: formation enthalpy of benzene, carbon dioxide, and water. Okay, so this is the normal equation I have just written for your practice. So what are the products? As products, we have 6 CO2 and 3 H2O. As reactants, we have 1 benzene and 15 divided by 2 O2. I'm just writing everything so that products. 6 times formation enthalpy of carbon dioxide and 3 times formation enthalpy of water. Then reactants, 1 time formation enthalpy of liquid benzene, 15/2 times formation enthalpy of O2. So these two supposed to add, then get the difference between these two. Do the substitution, get the answer. Even for the final exam, they are giving marks for this. Just you have to show it here to convince them that you have the knowledge that formation enthalpy of constituent element is 0. So the second method is the equation method. That's again very easier. In equation method, we are writing all these given equations. Okay, they are not given this equation. We have to build this up. Okay, this is combustion, mean excess O2, products are CO2 and H2O. So the second method is the equation method. Again, the very first step is to write this equation for the given question. Question is the combustion of benzene, so that I'm writing the question equation. And then, since they were given formation enthalpies, I'm going to build up all these equations for different formations. They have given benzene formation, carbon dioxide formation, and water formation. How do you form them? From constituent elements in standard state. So carbon and hydrogen for benzene, carbon and oxygen for carbon dioxide, hydrogen and oxygen for water. Then you balance them so that you are making these 3 equations for formation enthalpies. And then in front of that, I'm just writing the data they were given. Then my next target is to get this given equation, the question equation, from these different equations. So I'm going to make this question equation from this. So in that path that I can see, I need 6 CO2, but in the second one, I have only 1 CO2. So that I have to multiply this by 2. So the equation, multiply this by 6. So that equation number 2 multiplied by 6. Go on. I need 3 water, but here I have only 1 water. So that equation number 3 I'm multiplying by 3. So that third equation multiplied by 3. And then Benzene is the reactant, not the product. So I had to write it the opposite way. If you do this, if you go through that, you can end up with this equation. So I'm doing same to these values. I'm doing same to these values. Since I've multiplied equation number 2 by 6, then this value multiplied by 6. Since I have multiplied equation number 3 by 3, this value I multiply by 3. This is, I have written as opposite, that is negative. So 84 become negative 84. Get the answer. You can get the answer very easily. Okay, now we have the knowledge of these three. Writing equations. 2, thermochemical cycle and energy level diagram. Now I'm using these three equations. So the first one is a thermochemical cycle, concentrate well. Again, 95% of time for energetic questions, you are writing the given questions equation first, but not always, usually not for dissociation enthalpies. I'm just writing the question. Then the second step, if I analyze these other data, they were always given this formation enthalpies. How do we form them? We form them constituent elements. So we form one of these side using constituent elements. Going with benzene is easier. So that I'm making that first. So benzene you make with carbon and hydrogen. So that I'm just writing carbon and hydrogen. But still, the equation is supposed to be balanced. So I need to write this part here as well. Then whatever these equations, all these are balanced chemical equations. So I'm going to balance. This is products. These are reactants. Then I need 6 carbon and 3 H2, 15 divided by 2 O2. Then if you just need to check because now it's already balanced. So from this you can make 6 CO2 and also 3 H2O. Now we have the balance equations and with a cycle. Okay, so what is the final target, final destination? This is the final destination. How do we know that? See, all these arrowheads are pointing to these two. So this is the final target. Then what is the initial reactants are these? That you can see all these arrow tails have started from blue one. Okay, so now we know the initial and final. Now we need two different paths. One path going from coming to benzene and benzene to CO2H2O. The other path directly from constituent elements to CO2H2O. So we have two different paths. One path coming from all the way through benzene. The other path directly from CO2 and H2O. So two different paths. First path and second path. Okay, as a state function, first path, second path equals. So that I am equalizing this plus this. That is benzene formation and combustion enthalpy of benzene to this and this. Formation enthalpy of CO2 and formation enthalpy of H2O. Then subject the unknown combustion enthalpy, you can get the answer. It is this easy. Okay. Then again, I can show if you go here that you would see two different paths from here all the way here to here and here. Two different paths, the blue path and pink path. starting from initial to final. So when we are drawing this energy level diagram, we are using this full knowledge. I'm starting from, I would start from constituent elements because that is a 0 level. And I'm drawing this diagram, I'm going to go back, see. If I start from 0 level, negatives are greater, like 2 negative, and 1 positive, and also positive value is less. So when I'm drawing this 0 level, I'm making 2 more to the top. Guys, just give me a minute. Okay. පන්ති කියන්නේ මේ මම යාළුවනේ මේ recording සබයක් තමයි ඒක. It's okay. මොකද ප්‍රශ්නේ? ඔව්. ඔයා බය වෙන්න එපා. ඩොක්ටර් රොෂාන් පරණමාන. අපේ අක්කගේ නෙමෙයි මට මතකනේ ඔය දෙන්නගේ නෙමෙයි අම්මගේ කරා. ඔව්. එයා ගොඩක් talented ඉතින්. අපේ පොඩියගේ චුටියක් කීවා බය වෙන්න එපා අපේ පොඩියකට nothing happened. No issue. ඒකට heart attack නෙවෙයි. heart attack එක කාකිය විතරයි ඉතින්. ඕක අපි බලන්න මමත් කාලෙදි කී අපි දෙන්න චෙක් කරනවා කියලා. කලාවද? දැන් මොකද වෙන්නේ? මම ඉස්සර කරලා ඉන්නවා. හවුද? ඔව්. නෑ අවුලක් තියෙන මෙහෙමයි චුටියක් කි. බර්ස් වෙන්න පුළුවන් දේ තමයි අවුලක් තිබුණොත් ඔයාලට ස්ටෙන්ට් එකක් දාන්න. ඒක නෑ අස්තතු වෙන්නේ. කිසිම ඉෂුව එකක් නැතුවට ස්ටෙන්ට් එකක් දාලා යන හම්බුනොත් අර රීබෝල් එකක් වෙනවා ස්ටෙන්ට් එකෙන් පස්සේ සමහර වගේ අදිත් නැතිලා ඒ සමහර අදිත් තියෙන බ්ලොක් සා වෙන්නේ. ස්ටෙන්ට්ස් දාපුවාගේ මම ඔය තරම් ඉන්නේ අර ඩිපෙන්ඩ් එකේ අම්මා ස්ටෙන්ට් එකක් දාලා තියෙන්නේ කල්පෙට කලින්. අපේ ඔයා වගේම අපේ ගමම කරලා ගිහින් පෙන්නා මේ ඉතින් එජුකේෂන් එකේ ඒක ස්ටෙන්ට් එකක් දාලා හදලා දැන් මතක නැහැ ඒ ස්ටෙන්ට් එකක් තියෙනවා කියලා. අපේ අමරත් මේ අනුරෝසු ගන්න කියලා අපකට මතක නැහැ දැන් ස්ටෙන්ට් එකක් තියෙනවා කියලා. ඕක කරලා නටන්නේ. ඔව් දැන් මට ඡන්දය ගන්න නැහැ කවර. දැන් ආයා ලොකු වෙලා දැන්. ඒක නිසා ඔයා හිතවරක් කරගෙන නැති වෙන්නේ එච්චරයි. හිතවට ගන්න නැති වෙයි. ඔව්. ඔයාට කීයද එන්ජින් වෙන්නේ? දැන් මම ඉන්නේ ඉන්නේ මම කීයද එන්ජින්? ඉතින් ඒක එන්නේ නැහැ. ඔව්. දැන් ඔයාට ඉන්නේ යන්න පුළුවන් කොච්චර යන්න ඕනද ඊට පස්සේ? يعني ඇඩ්මිට් වෙලා තියෙනවා මේ එන්ජින් එකේ උනා. ඔව්. ඔව් නෑ ඒ විතරක් නෙවෙයි දැන් බැලුවා ඉන් කේස් මොකක් කරොත් ඒක පිළිගන්න බෑ. ඒනාට චුට්ටක් නෙමෙයි. ඔයා මේ worst case එකේ නම් send එක දාන්න කියලා හිතා ගන්න දාන්න මට ඔක මොකද දැනගන්න කියලා. මම හිතනවා කැම්පින් ආව ඒකට දාන්නයි කියලා. ඒකට ඒ වගේ එකක් ඔයාලට හරි. අපි ආවේ ඒකට නම් ඔයාලට මාර රිලීස් එකක් දැනෙන්නේ ඔක දැනගන්න පස්සේ. අපි රිලීස් එක කියලා හිතාගෙන. Okay, I had to answer that phone call. I'm sorry for that. Anyway, we are starting. You can just go on and you can see then. Okay, so yeah, I was just saying, since that positive plus negative values are greater, I'm just gonna place my 0th level to closer to the top. Then I have two different paths. I'm going with that. This is your y-axis. You are not calibrating the y-axis so that you are not touching all these levels. The y-axis, see, you are not touching. You are not touching any of these. Okay, my first step is going to be this 0 level. So this is a 0 level. I'm just writing everything in 0 level. Then I suppose to have two different paths. Constituent elements to CO2, H2O. Constituent elements to benzene, benzene to CO2, H2O. Whatever the given values, I'm just going to go with that. As a standard, I'm always going with, first I'm making carbon dioxide, then I'm making water. Okay, first I'm making carbon dioxide. So this is the formation enthalpy of carbon dioxide. Since I'm making 6, I have to multiply here with 6. Since I have made carbon dioxide, rest of the part after I made the carbon dioxide, whatever the part, I'm just writing here. Okay. Then remaining is H2 and O2. Then second step is I'm making water. I'm just writing same CO2 here. And then from here, I'm making water. So this is the formation enthalpy of water. Since I'm making 3, it's multiplying by 3. So these are negative values. So that going down. And then, so my first path is done. My one path is done. I came from constituents to CO2, H2O. My second path, I'm coming to CO2, H2O through benzene. But that is positive. So I'm making benzene from constituent elements, and that is this level. I'm making benzene, that is plus 84. From benzene, then I am burning benzene to get same CO2, H2O. Same CO2, H2O. Okay. So combustion. Now I have two paths. See, first path came here. This actually is another version of thermochemical cycle. Remember, all are balancing to each other. Why I'm each other? So okay, then I have two levels, top level and bottom level. Between these two levels, this blue lines together, or then this green line, supposed to be equal to each other. These gaps are equal to each other, but these two supposed to go down to one direction. Then you see this is this orange part is in the top level, like going upward. So I'm going to go that with negative then. So this is, I can just write as it is. So that carbon dioxide, I can just write as it is. Water, I can just write as it is. Combustion enthalpy, I can just write because all are going down. Since this is going up, I am making it the opposite direction. So that I am writing carbon dioxide into 6, water into 3, negative benzene formation. So you can get the exactly same value. If these 4 methods are comfortable, then rest of the part is really easy to understand. So the second method, I don't like this method because here, looking at this sign, we cannot just determine the sign looking at the doing this calculation. Then you have to background check with this sign. So better go with the first method. Question number 5. If you still feel uncomfortable, do this. 6, 7, 8. Okay. Question number 8. I'm going to do that. So this is another type of enthalpies, that is dissociation enthalpies. Question is, find out standard enthalpy of combustion of methane. Okay. Data, or they were given dissociation enthalpies. Standard dissociation enthalpies of what? CH bond, OO double bond, CO double bond, and OH bond. Okay. Equation method, not that much applicable. If you want, you can go with that. So usually we are going with thermochemical cycle or energy level diagram. And what is the first step? First step is to write the equation for given question. Okay, question is CH4 plus oxygen gives CO2 and H2O. Then since they were given dissociation enthalpies, I want to make sure which bonds are dissociating. So that to see these bonds, I'm writing these with sketches. Skeletal structure would be enough. You don't want Lewis or you don't want Vesper shapes. So 1, 2, 3, 4, you are breaking 4 bonds here. 1 double bond, but 2 of them you have. 1 and 2, 2 CO double bonds. 1, 2, but you have 2 here, so altogether 4. What are you making? You are making gaseous constituent elements. Gaseous constituent elements. Then here into 4. CH dissociation into 4. Here OO dissociation into 2. Here CO dissociation into 2. Here OH dissociation into 4. Okay, so once you written those symbols, then go with real values exactly the same. So once you get these values, you can just substitute this. It's not necessary writing these symbols twice in your answer, but I have shown them here. That's for your practice. Again, this is through the Hessel's law. Let's see what is the final stage. See, you can see clearly all these arrowheads are pointing to this. So this is the final. What is the initial? This blue. This is the initial. See, all these arrow tails are starting from this blue set. So there are 2 paths. One is making CO2H2O, and then from those CO2H2O, you are coming to dissociation. Or the second path, the green path, directly you are coming from methane plus O2, you are coming to constituent elements. So 2 different paths, orange path and yellow path. We're going to make these 2 paths equalize. So this path, what do we have in this path? Red path. And then green path. What do you have in this green path? If I go with red path, number 1, combustion. This is number 2, dissociation of CO. Number 3, dissociation of OH. Green path, number 1, dissociation of CH. Number 2, dissociation of OO. So, combustion mean I have given this number 1. Number 1 plus number 2 equals, so that CH dissociation number 1, then OO number 2, these two together. CO, and this is number 3, OH. 1, 2, 3 equals 1, 2. Just do the substitution, get the answer very easily. This is dissociation. Knowing that, we're going to go to energy level diagram very easily, knowing these breaking bonds and forming bonds. Breaking bonds are you are breaking CH bonds and OO bonds. You are making carbon dioxide and water bonds. So just do the substitution. You can get answer very easily. Answer is minus 788. Keeping everything in your mind, I'm going with this energy level diagram. Here I can start from constituent elements because here you don't have constituent elements. Oxygen is in its constituent level, but carbon and hydrogen are in these gaseous atoms. So it's totally different. Okay. Then I'm going to start from here. This is my starting point. Anyway, you're not putting any 0 here. This is not 0 because this has formation enthalpy. So I'm starting from here. See, I have 2 paths starting from here. Starting from here. This is the first path and this is the second path. I'm going to go through that again now. In energy level diagram, see, all are connected to each other. If you identify these connections going on with energetics, is extremely easy. So from here, I'm going the first path. I'm breaking CH4 so that it is delta H theta DCH. Then there are 4 bonds. Then I'm breaking O2 and that is this. Once you break CH4, you're only writing it is constituent elements and keeping this O2 as it is. Then when you are breaking this O2, so you are just writing it is constituent elements. Then dissociation of 2 OO bonds, and this is the value. So this is the first path. Then again, I'm going to come to this, burning CH4 and then making it. How do you know that burning of this is combustion is negative value? That you know from previous calculations. Sometimes, remember the very first one we did for formation enthalpy, so that we didn't want this combustion enthalpy to get this arrow direction. But here we don't know the arrow direction unless otherwise we calculated here. Usually we know the combustion is negative, so you can go negative. Sometimes you need this when you're doing lattice. Lattice can be the negative or positive with conditions in some cases, not the lattice dissociation, okay? These questions, so that you should know to which direction you are drawing this one. Again, we can get this is negative because we know combustion is negative. Otherwise, we have to go back and calculate this from thermochemical cycle or if it is possible with state function method to get this. We know this is negative, so we are coming down to burn these two to get CO2 and 2H2O. Then I am making all this. I am dissociating all this. So I have then CO2 dissociation, 2 CO bonds. Then water dissociation, that 4 OH bonds. 4 OH bonds. See, 4 OH bonds. Okay. So now we have, once you're done with that, exactly same path that we did earlier. Now you have 2 levels. Here that you can see, this is going up and this is going up, this is going up, and this combustion is going down. So you can make it negative and later make it positive. So whatever the way you can go on, you can just write here this negative C. Then you can get the answer with the correct sign. You can understand that we did questions. Number 9, 10. This is again something really important. Here, they are asking the formation enthalpy of sodium chloride given different data. So whatever the data they were given, so I'm going to build up. I'm going to go, whatever the method we are doing, we need this. I'm going to build up this knowledge, these equations for these given data. So the first one they were given, lattice dissociation enthalpy of sodium chloride. So that is sodium chloride solid dissociating to sodium plus gas and Cl minus gas. I'm just writing the value here and the symbol for your practice. Then the next one, sodium sublimation, that is sodium solid goes to sodium gas, then the value, and then this still the symbol. First ionization energy is sodium, very easy, we can write. Sodium gas is going to sodium plus electron, the value and the symbol. One dissociation enthalpy of chlorine, Cl2 goes to 2Cl, that is this, and then this value. Then the last one, electron gain energy of chlorine, that is this, and this is the value, and then this is the symbol. Okay. Always, the very first step is supposed to be writing the equation for the question. What is the question? Formation enthalpy of sodium chloride. Standard sodium chloride is in solid state. So you are making it with sodium solid and half Cl2 gas. Okay. Then my second concern is making this equation using these equations. Okay. I need sodium solid. Yeah. I can just write one sodium. One sodium is here. I'm just writing 3 here. Then I need Cl2 but half Cl2. So that number 5 I divide by 2. Divide by 2. Number 5 divide by 2. That's done. Then what else I needed? I need 2 to the other direction because sodium chloride is a product here and I had to write it negative 2. When I'm writing number 3 sodium, with it, it's coming sodium gas that has to cancel off with fourth one. So just I'm adding fourth one. Then when I'm writing chlorine, I'm going with this Cl minus to cancel that. I have to cancel this. Then I can cancel off Cl minus as well. That is again number 6 plus. Cl minus is getting cancelled with this. Sodium plus is getting cancelled with this. So this is the way I'm supposed to go. I'm doing exactly same thing. to these numerical values that you know how to go with equation method, so you can get the answer very easily. It's minus 448. Then thermochemical cycle of ionic compounds is called von Haber cycle. Only the word is there. Okay, there are two different methods. We can show these each of these equations together, each of these equations separately. If you practice with this one, this is exactly the energy level diagram if you draw y-axis here. But they would ask both different methods. So far they were not. You can go whatever the free way. So this is again going with these equations that we already did. So again, I'm going to start from this formation. Okay. So formation means starting from sodium solid and half Cl2. I'm going with one by one. Either I can go directly with sodium, then I can go separately with chlorine, or otherwise sodium once, chlorine again, so on. It depends. So I'll show this one. I think this is, you can understand easier. But if you practice with the other one, that's easier to go with energy level diagram. So this is the initial level formation. Sodium solid has to go to sodium gas, sublimation. Chlorine half is going to dissociation to get chlorine gas. I'm going with two different colors so you can understand easily. Chlorine, dissociation, that is going to chlorine gas. Sodium again, gas supposed to go on to this sodium plus gas, ionization. Then chlorine supposed to go through this Cl minus through electron gain. These two together has to make sodium chloride. How do we know this formation is negative? We know this formation is negative, that we done with equation method. Unless otherwise we don't know. Now we know it is negative. So that using these two, I'm making sodium chloride solid. And also using these two lattice, I am making sodium chloride. See, I have all the arrowheads are pointing to red. All the arrow tails are starting from this green place. So that I have two pathways, the purple path and blue path. Purple path, how many do we have? 1, sublimation, dissociation, 3, ionization, 4, electron gain, and 5, lattice. The other way around, we have only one single data, that is the formation number 1. So we can say orange color number 1 equals purple color 1, 2, 3, 4, 5. Just do the substitution, get the answer. Okay, this is exactly same. See, the separately you are just writing here. First one is sodium solid to sodium gas. Then second one is Cl2 to Cl gas. Sodium gas ionization sodium plus. Okay, we came there. And then what happened? So Cl2 gas here existing as it is. Then you are just staying as it is, because in this step you are only changing this sodium. Then sodium becomes sodium plus plus electron. Cl gas is just existing as it is. Then sodium plus gas just existing as it is. Cl minus, sorry, chlorine with electron making this Cl minus. Okay. Now the difference is here plus information we are giving to the upward arrows, giving with upward arrows. Minus information we are giving with downward arrows. And we should know that the electron gain energy of chlorine is negative, and they are giving it as a data. So that's negative, so we are writing it down. Then from these sodium plus and Cl minus, we are making this. Before that, we know this is negative, so we can write this NaCl solid to negative direction. Again, one path and the second path. All these together, one path. And this is the second path. Equalize them and get the answer and see. This is from your resource book. Just I have done with sodium chloride. They were done with lithium fluoride. Still the same. Okay, the next method is the enthalpy energy level diagrams. Again, I'm starting from this. I'm going with sodium sublimation, sodium first ionization energy, sodium solid to sodium gas to sodium plus gas. All the time, half Cl2 gas is just existing as it is. Now I'm going with working on chlorine. So chlorine first one is dissociation, but it has to come down for this electron gain energy is negative. Now we have, so that is done. Then I'm coming down here to make this sodium chloride. This is I'm making sodium chloride. I have another path to make sodium chloride, and that is from here to here. Using sodium plus and Cl minus, I am again making sodium chloride. Then again, I have two levels. Energy level diagram going with levels. See, whatever the direction you want, this, and this plus. These, so that become negative. Just do the substitution, get the answer. This is not theory. I read it theory very well. In magnesium, the only difference is, other than this magnesium gas going to magnesium plus, this is going to magnesium 2 plus. That's a second ionization energy. So that you have two negative charges. Difference with aluminium mean aluminium first ionization, second ionization, third ionization. So oxygen has first electron gain, second electron gain. Born-Haber cycle, you can just draw whatever the way. But enthalpy energy level diagram, that we know, oxygen's first electron gain is negative. Second electron gain is always, for whatever the compound, is positive. Knowing that from our background knowledge, that we know 2, 15, 18, other than phosphorus of group 15, this is positive. All others are negative. Oxygen is group 16, so that first ionization, oops. Oh, that's magnesium. I don't want magnesium. I want this aluminium. See? So that Eg1 negative going down, Eg2 positive, so going up. But when you're writing this, you just write these additions because they were given symbols. You need the real values to get the answer. And they would never do like this level equals this level. You cannot do that because there is this overlapping little part. Entropy. Entropy is the randomness, disorderness. Entropy equals reversible reactions, heat change divided by temperature. So the units become joule per Kelvin per mole. Entropies, this is how we decide the entropy is negative or positive. Going from more movable form, solid to liquid, liquid to gas is more movable. That's entropy increasing. Or otherwise, going from less movable physical state to dissociate to more movable physical state. So this has only physical change, but this has this chemical reaction going from solid to gas or liquid to gas, solid to liquid, whatsoever. Going the other way around, entropy is decreasing. So entropy same as enthalpy. Enthalpy negative is more prone to spontaneity. Entropy positive mean spontaneity. But still, we have to go with enthalpy as well. Not like enthalpy, there is no zero entropy for whatever the compound unless it is in this perfect crystalline solid state. So liquid form, again, there are these entropies that we define with respect to aqueous H plus mobility. We didn't understand. As a state function, we can calculate entropy very easily. So this given question, you can calculate entropy very easily for this reaction. So the given reaction, formation of ammonia. So I'm writing the formation ammonia equation. Then product entropy and reactant entropy. You guys know how to do it as a state function. Just go on. I don't want to make this revision one very, very longer. Okay. So question number 13, 14, just go on. Then moving on to Gibbs free energy. Delta H equals delta D equals delta H minus T delta S. Okay, how to get Gibbs free energy units? Kilojoule per mole, Kelvin temperature, joules per mole per Kelvin, Kelvin per Kelvin cancelling off, joules per mole multiplied 10 to the power minus 3 or so. You can get with kilojoules per mole is the Gibbs free energy unit. This is really important. Gibbs free energy negative, spontaneous, positive, non-spontaneous, and this is equilibrium. In equilibrium condition, we are coming across again with this. In equilibrium, when the equilibrium, when something is in equilibrium, so or the equilibrium constant equals to 1. So same condition, this is in equilibrium. So, but the K is very, very greater than 1. That is spontaneous. Equilibrium constant very, very less than 1. That is non-spontaneous. Get this correlation once we're done with equilibrium. This is the way we find the Gibbs free energy as a state function. You guys know that. Okay, so I have done all these questions. Just go through these questions, do a couple of these. Whatever you get the value for one reaction, opposite is the opposite of that. It is same for Gibbs free energy as well. Here, this dissociation of AgCl is positive, that is non-spontaneous. So that we can say a precipitation. Precipitation is spontaneous. We know silver chloride is a good precipitate that we are using to identify silver plus and Cl minus in inorganic chemistry. Disadvantage is it's not giving any hint about the timing, even it's spontaneous or not. Okay, I'll explain one example here. Let's say I'm going with this. Looking at these given data, you're supposed to understand this, okay? In given data, third one I'm taking, delta H is negative, delta S is negative, delta G is positive. What is the condition for that? That condition is non-spontaneous at high temperature. That's because, okay, this is negative. Let's say this negative value is high, negative 10, positive 4, answer is negative 6. So then delta G become negative, so it's spontaneous. Okay, but let's say this side is negative. This side is larger. Okay, this side larger mean now this is negative, that's all right, but this is larger mean delta S, supposed to be, so here the delta S is negative. So this negative value multiply this negative value of temperature, this given equation multiply this negative value of entropy, negative multiply negative become positive. Now this side is positive. So this is positive. Let's say positive 10, negative 4, answer equals positive 6. So it is non-spontaneous. To be this part highly positive, entropy we cannot change. Entropy is constant. What can we change? Temperature. So when we increase the temperature, this side become more and more positive. Then delta G become positive. So non-spontaneous at high temperature. This is the way you define these observations with the equation. Some are using a pie chart, but I guess this is more easier for you to understand. Again, I did a lot of questions. You can try these questions, even question number 23. It's from this modern papers 2017. Just to convince more about this. And this is the summarization of resource book. Okay. I am doing everything to bring you this higher successness. This is your dream. My dream is to bring you about 29. So 29 is not, it's sort of a harder target, but just practicing with, it is never become harder. So I know you guys can do better than that because I've guided them. And these Sinhala students, they went to some other classes, but these English medium students just stuck to me and they are in this higher successness. One of the reasons that English medium students are coming to this higher successes is brain supposed to be there, but the other reason is they are going to controllable level classes, control classes, so that single medium students don't have enough study time. These two students are really talented. And this boy's brother came to me. He's in a medical faculty, and this boy's dad is the Ratnapuras, this, you guys know Nimri, heart surgeon's son. They are really talented. They said me they never thought this would happen. They never thought that English medium students can challenge them. See, you can win. Stick to the path. Let's do this together. Only request I'm doing is stick to the path. Whatever I'm asking you guys to do, just go with that. That's all. Okay, bye. Take care, everybody. Then from the next recording, I'm starting to do these questions. Bye. Take care. Buddha Saranai.